This is the first example for the velocity diagrams from your notes. So what we're going to do is to establish the velocity of various points on this link and be able to draw what they call a velocity diagram. For these I have a pivot point here at A, a crank which runs out to B, so B is rotating around A. This thing says that it's rotating clockwise at 40 radians per second, and I have a piston which is sliding backwards and forwards on a connecting rod. I have a point G here which is the centre of mass, which we'll refer to later in the question. Okay, first one I want to do is to establish the velocity of the known things. So in this case we know that this link is rotating at 40 radians per second about point A, in which case B will be travelling at 90 degrees to the link. So this will be the velocity of B relative to A. So quite important, I drew my arrow at B, therefore it is the velocity of B relative to the other end of the link, which is A. Okay, I can establish this velocity. VBA is equal to omega r, which is equal to 40 times 0.3 meters, which is 12 meters per second. Okay, I can now draw this vector. I know my vector will be at 90 degrees to this. So roughly for my example, about 90 degrees. Come down and draw my velocity vector, 120. Okay, this is, as our label said, this is the velocity of BA up on here. So I label this VBA. I know the arrow goes this way, so I know my arrow is going that way. And with all of these things, the arrow points to the first letter. So B must be at this end and A must be at that end. Okay, I now know point A, which is my fixed point. So I'm starting from there. I have established point B. The next one I need to establish is point C. Everything on a linkage system must be joined to two independent parts. So in this case, C is connected to B, and C is also held by these slides. Now these slides are stationary. A is a stationary point, so I can label any point down here as also A, because they all have the same velocity, they are all stationary. So C is connected to B, and C is connected to A. So in these things I'm looking for, I now need to find C. So I'm looking for VC something and VC something else. So we said C is joined to B and C is constrained by A as well. So I'm looking for VCB and VCA. CB is a link. Therefore, from what we've done in class, we know that one end of a link can only travel at 90 degrees to the link itself. So 90 degrees in here, VCB. Now I won't put an arrow on there. I may be able to guess which way it's going, but I'm not even going to try. At 90 degrees to there. I also need VCA. VCA, C relative to A. It's not a link. C can only travel backwards and forwards along the slider. So VCA must be a horizontal line. VCA. Again, I drew my velocity at C, so therefore it's VC relative to something. I drew it at C, VC relative to something. Velocity diagram is quite simple. I now just use these two lines to find point C. So CB must be a line that passes through C and B, and I know where B is. B's there. So 90 degrees to my link. Take that across, draw that through B. This is going to be VCB, could be up or down. And I also know CA will be a horizontal line through here. So I can put through A through here. So this is VCA. C must be on this line and C must be on this line. So this point here where these two cross must be point C. We've labelled this. Up here we labelled it as VCA. We've labelled it VCA down here, and we know that the arrow points to the first letter C. There's C, arrow must go that way. VCB, arrow must point to C being the first letter. The questions want to know up here, find VCA. They want to know the velocity of the piston. VCA is this one in here, 12.7 on my little sketch. I think it's about 12.2 if I did my sketch a bit better. 12.7, I think my notes actually say 12.2 because I did it a bit neater. We also want to know omega BC, so the rotational speed of BC. So omega BC will be equal to V over R, so it'll be VBC over radius BC. VBC, measure that. This one comes out at 6.35. So omega BC will be equal to VBC 6.35 over radius BC. BC is 900 millimeters long over 0.9, giving me 7.06 radians per second. Okay, and which way is it going? Up here, I've got a vector. We're talking about link BC. BC is here. I have got here VCB going downwards. VCB was this one, VCB, drawn at C. That arrow here is downwards, so this arrow here will be downwards, which means that this link will be rotating that way about B. So this link will be rotating omega that way. So whether that's CB or BC doesn't actually matter. It's still rotating in an anti-clockwise direction. Okay, and the last one they want to know is the velocity of GA. G on this is the center of mass. We need that to do inertia forces with. Quite simply, G is 1/3 of the way between BC. So simply on these diagrams here, that's going to make this point 1/3 of the way between there. So take that, measure it, mark it, and point G will be 1/3 of the way between BC, closest to B, closest to B. What the question's asking for is what is VG relative to a stationary point. So I'm looking for GA. GA will be going in through this way. And if we measure that off, VGA is 11.7 meters per second.